29? All right, guys, the first thing that we are asked to do is write a balanced equation for the reaction between hydrogen and oxygen. Suppose that 4 molecules of hydrogen gas and 4 molecules of oxygen gas react to form water, right? So we know how to do this. We've got 4 molecules of hydrogen gas. So we've got 4 H2s plus, my screen is frozen, plus 4 molecules of oxygen gas react to form water. Is this balanced? How much water can we make if we have 4 H2s and 4 O2s? Some. We can make 4. What's the problem with this? We have extra oxygen. Oh no! How much extra? Really?
2.
2 what?
2 oxygen gas.
Yeah, we have extra 2 O2s. Okay, so generally when people are drawing chemistry stuff, we use red for oxygen and we use black for hydrogen. Just because. So let's see. I'm gonna draw this, not to scale, but I'm gonna draw everything here. So I'm gonna draw my 4 hydrogen molecules. So here you go. Use black for hydrogen. Use black for carbon too. Okay, so there's my 4 hydrogens, and here are my oxygens. We haven't really talked about this, but oxygens are actually bigger than hydrogens. Did you say you made them smaller?
Yes.
Just for funsies?
Yes.
So do you guys see how that represents the reactant side of my equation?
Yeah.
Bien. Okay, so now I need to draw my 4 water molecules, and each of my water molecules is going to have an oxygen and 2 hydrogens. So it's going to look like Mickey Mouse ears. Okay, so here's all my 4 waters. But I have 2 oxygens left over. Sorry, 2 oxygen molecules left over. So I'm going to draw them too. We've never drawn equations like that before, right? Where we had stuff left over.
Right.
Yeah.
That's kind of weird. All right, so then we've got some questions down here. How many molecules of water can be produced? Or which reactant do we have extra of? Of O2. Why?
Because we didn't have enough hydrogen.
Yeah, we ran out of O2 or H2. Sorry, O2. H2. We ran out of H2. How many molecules of extra reactant are there? 2. Everybody on the same page so far? So far, so good. All right, look at this. Construct a before, change, after table for this reactant mixture. I know you guys love these. Okay, so we've thank you. So we've got our 4 H2s plus 4 O2 yields 4, yes, arrow, 4 H2O plus 2 O2. So normally we would put moles in our BCA chart. We're just going to put number of molecules in this one, right? Because the number of moles would be quite small. Okay, so before we started with 4 of these, right? And we started with 4 O2s. And in our before box, we have 0 H2O. This is kind of weird though, because it's the same, but we're just going to say that we have 0 over here. And then what changed? Did we use up all 4 of our H2s?
Yes.
We did. So we used up 4 and we had 0 left over. How many of our O2s did we use? We used up 2. And we ended up with 2 left over, right? That's kind of weird because these are connected. I'm just gonna roll with it though. How many water molecules did we produce? We got 4. And how many O2s did we produce? That's like, this is like strange, right? Just to write strange here because it's over here. Like we just didn't, like those exist because of this, right? So really our equation is kind of, it's kind of weird. We're just going to go with, it's just kind of weird. What? You don't like it? I don't know. It is strange, right? Like the other way you could say it is that we used all 4 here and we gained 2 over here, which like maybe, right? Anyway, this is like, this one is kind of weird, but I think you guys will get the idea. So then there's questions on the next page. How many waters of molecules? How many molecules of water could be produced? 4. Which reactant is in excess? The O2. Why? Because we ran out of. It's the same answers, isn't it? I know, we just did it 2 different ways. How many molecules of extra reactant are there? 2. All right, so what determines how much product can be made from a particular reactant? Kinda. Charmaine said how many reactants there are.
The formula of the product.
Yes, you're gonna look at your formula, right? We're gonna figure out how much this is. So here's another way. Let's see. There's probably a better way we can think about this too. Like this is balanced, right? But it's kind of weird. Can we change some things? Because this is strange, right? We can't really say that that's a product. It's just leftover reactant. Do you guys see that? So what did you think of this equation when we wrote it?
I mean, can we just knock off the end?
You don't like this part? Okay, so let's take this part off. And then how do we write a balanced equation? Because we wrote this based on what they told us would happen, right? So we get rid of that. Is this balanced?
No.
What's wrong with it? Some people said yes. Do we have lots of yeses? We had a few no's.
Can we just take away some oxygen from the reaction?
Okay, so if we take away some oxygen, how much do you want to take away?
2.
I'm going to take away 2. So we're going to change this so that it says 2. Now we have 2 O2s. So far, so good?
Yeah.
So now if we take a look at this, I'm looking for something that's blank. We know that before we started with 4 moles of hydrogen and 4 moles of oxygen and no water. Actually, you guys see this up here. We could edit this some more. Do you guys see how we could edit it some more? We're gonna divide everything by 2. So I'm gonna make this 2H2O. Sorry, 2H2 and 1 O2 and 2H2O. All right. So if we start out with 4 of these and 4 of these and 0 of these, and we want to know how much water we're going to produce, right? How much water could we produce considering this equation if we start with 4 moles of hydrogen? Right? This is a 2 to 2 ratio. Should we be able to make 4? Do we have enough hydrogen to make 4 moles of water?
2 moles.
We have enough to make 2 moles? Where'd you get that?
Like it was too high.
So if we start with 4 moles of H2, because that's what this number is telling us down here, this 4. And then we're going to convert this with, for every 2 moles of H2, we can make 2 moles of water. How many moles are we going to make?
1.
We're going to make 4 moles of water.
I'm multiplied by 4 times 1.
It's 4 times 2 divided by 2.
Oh, okay.
So I appreciate your enthusiasm if you're like it's Monday morning. This is a tough day to do that. All right. So then the question is, and this is what our answer would be if we said that we had oxygen in excess, right? If it didn't matter how much oxygen we have, we would say we're definitely going to get 4 moles. If we take a look at the zone, we said, okay, I've got 4 moles of oxygen. for every 1 mole of oxygen, I can make 2 moles of water. How much could we make? We can make 8. So which one is it going to be? 8 or is it going to be 4? Why?
It's a smaller number.
Because it's smaller. Well, why does being smaller help it?
It will run out first.
Yeah, we're gonna run out. Ooh, we're gonna run out of hydrogen before we run out of oxygen, right? You have a question, Luke?
Nope.
Okay, you're just waving back there.
Yeah.
So we're gonna say, all right, we're gonna make 4 moles of water, and that's gonna have us using up all 4 moles, or we're gonna use up all 4 moles of our hydrogen. But how many moles of oxygen are we gonna use? How do we get this -2? Like we looked at the picture. But if we didn't have the picture, how can we do it? If we're gonna make 4 moles of water, and we know that for every 2 moles of water, we're going to have 1 mole of oxygen gas, right? 4 times 1 divided by 2 is going to give us 2 moles of oxygen. So that's how we're going to figure out how much oxygen we're going to use. And then at the end of our reaction, we've got 2 moles of oxygen gas and 4 moles of water. Is that what our picture shows? Yeah, we've got 1, 2, 3, 4 Mickey Mouse here, waters, and then we've got 2 oxygens. So that's how we can do it with the BCA chart. Right, so when we see these on both sides, this is kind of like an algebraic expression, right? If you saw this in algebra class and it was something like 4x plus 4y equals 4z plus 2y, you could simplify that, right? You would take the y and subtract it from both sides, so that you would only have x's and y's over here and then the z over here. It's the same kind of thing. It's just an algebraic thing that you just did. So we made a table that described that reaction. Doesn't describe oxygen as a reactant or as a product because it's not really a product. It's just leftover stuff. All right, so based on our 2 methods of analysis, what determines how much product gets made? Which of these 3 things determined how much product we could make?
The hydrogen,
The hydrogen? Why the hydrogen?
because you need twice as many.
Because you need twice as many. So if you need more of something, that's what's going to determine what it is.
Yes.
Why no?
Because you'll run out of the other thing first.
Yeah. So the thing that's gonna determine how much product we can make is what we run out of first. What did you guys run out of first with the silver and the copper lab?
Copper.
You ran out of silver nitrate first, right? Because you had extra copper left over. So the thing that's going to determine that is what you have. I don't know. Let's see, less of, and this is important that it's proportionally, right? Because with this example, you had the same amount of hydrogen gas as you did oxygen gas. But the problem is that proportionally, when you have a balanced reaction, you need twice as much hydrogen as oxygen. So if you have equal amounts, you're going to run out of something. That's going to be a problem. Okay, I guess we'll try another one. Of course you do, Dr. O. Chemistry is the best thing to do at 9 o'clock on a Monday morning. Lucky you guys. It is 9 o'clock on a Monday morning. You want to sleep on? Fair. All right. Let's try to do this one better. Write a balanced equation for the formation of ammonia. What's ammonia?
Things the stuff I eat.
The thing that is mixed with H2.
Yeah, NH3. I did that once. I didn't know that rule. I did not die.
Why? Wait, why did you do it?
I don't know. Screwing around. It was in college. You do dumb things in college.
You're just like, oh, what should I do for fun? Let's just mix it.
No, we were practicing some demos.
Oh.
And we were using bleach and ammonia because you could use them to change the color of pH indicators. But anyway. All right, so we've got nitrogen gas, which is N2. hydrogen gas, which is H2. And we're going to make NH3. Is that a balanced equation? It is not. Let's see. These two are both even, so this one's going to have to be a 2. And that's going to give us 1 nitrogen and 3 hydrogen. Ta-da. Okay. It says given 6 molecules of nitrogen and 12 of hydrogen, make a drawing that represents a reaction container before and after the reaction. If you are a person who likes to get the colors right, quote unquote, the color for nitrogen is blue. All right, so I've got 6 molecules of nitrogen. 1, 2, 3, 4, 5, 6, and 12 of hydrogen. And I'm already not looking forward to drawing these, but okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, how many ammonia are we going to get at the end? How many individual nitrogen atoms do we have?
Well,
We have 12. If we've got 12 of them, how many hydrogens would we need? How many hydrogens would we need to be able to make 12 ammonia atoms? 36. Do we have 36?
no.
No, we don't. Which one are we going to run out of first?
Hydrogen.
We're going to run out of hydrogen first. So if we're going to run out of hydrogen first, how many hydrogen atoms do we have?
Why are we running out of hydrogen first?
24.
We have 24. If we have 24, how many ammonias can we make? 8. Okay, so if we're going to make 8, I'm going to draw my 8 nitrogen atoms where my ammonias are going to go. There's my 8. And then I'm going to give each of those 3 hydrogens. So that's going to use 24 of my hydrogens. Does that use all of my hydrogen?
No. Oh, yeah.
Yes. Does making these 8 ammonias use all of my nitrogen? How much do I have left? I have 4 left. 1, 2, 3, 4, 5, 6. Did I only make 6? I only drew 6 and no one stopped me.
What? Oh, you're only supposed to have six?
No, it's supposed to be 8.
Oh. I thought you just left the left side.
That's better. Okay, so now I have 8. 1, 2, 3, 4, 5, 6, 7, 8. So now I've got 2 nitrogen gas molecules left. Doesn't really matter where they go. So it says how many molecules of ammonia can be produced? I produced 8. Which reactant is in excess? N2. Because not enough H2. So the thing that we run out of first is called the limiting reactant because it is the reactant that limits how much product you can make. This is how many molecules of excess reactant are there? 2. All right, what questions do you guys have? You guys feel better about this one or worse?
Better.
Okay, a little bit of both. I'll allow it. It says construct a before, change, after table. Oh no. I know you guys love these. All right, so our equation was N2 plus 3H2 yields 2NH3, right? And we were told we have 6 molecules of nitrogen and 12 of hydrogen. We start with none of our product. So if we wanted to use all of it, this would have to exist in a ratio that was 1 to 3, which would mean we would need 6 moles and 18 moles of hydrogen. So that's another way to approach these. If you're looking for which one is the limiting one, see which one you don't have enough of to meet that ratio. The change that happens, we said that we were going to use up all of the hydrogen, right? So we're going to use all 12 of these. If we use up 12 moles of hydrogen, how many moles of nitrogen are we going to use? we're going to use 4. So those of you who didn't come up with that super fast by doing it in your head, if we have 12 moles of H2, we have to multiply that for every 3 moles of H2, we're going to need 1 mole of N2. And so 12 divided by 3 gives us 4 moles. So we used up 4 moles. All right, so this over here is 0. We've got 2 moles of nitrogen remaining. How many moles of NH3 do we produce? The number is going to be twice this number, because if we use 4 moles of N2, for every 1 mole of N2, we're going to produce 2 moles of NH3. So that's going to be 8 moles of NH3. 8. Is that what we got? 2 moles of nitrogen and 8 NH2s or NH3s at the end? Yeah. After Dr. O'Malley realized she'd only started with 6. Figured that out. According to the table we made, how many molecules of ammonia can be produced? 8. Which reactant is in excess? Which one do we have extra of? At N2. Why? We ran out of H2. Oh, I wrote H2O. H2. How many molecules of excess reactant are there? 2. Describe what you must look for in a particular reactant mixture to decide which reactant will be in excess. The way that Dr. O'Malley does it, I look for the ratios. And I look for the thing that I don't have enough of. So if this is a 1-to-3 ratio, so here we've got a 1-and-2 ratio to 3H2 ratio. But what we actually had uh, 6 moles of N2 and 12 moles of H2. And so since this is 1-to-3 and this over here is a 1-to-2 ratio, it tells me I don't have enough hydrogen. And so that's how I know which one I'm not going to have enough of. And so this one will be, I'll have extra of it. It will be in excess. Which is what happened. Are you guys ready to try these yet?
Yes.
Not 3.
Not 3? 3 is different enough? Okay. So 3 says when 0.5 moles of aluminum reacts with 0.72 moles of iodine to form aluminum iodide, how many moles of the excess reactant will remain? How many moles of aluminum iodide will be formed? So, excuse me, first we need to write our equation. So we've got Al plus iodine. Iodine is diatomic. Yields ALI. Is that balanced?
No.
What charge should aluminum have? Should be 3. What charge does iodine have? It's 1. So this is going to have to be a 3. Is our equation balanced?
No.
No. Because we got to make it an even number, right? So this has got to be a 2. So this will be a 3. Now are we balanced? No. What do we need? We need a 2 in front of the aluminum. Now are we balanced?
Yes.
Yes. All right. We've got 0.5 moles of aluminum. So I'm going to put 0.5 here. Reacting with 0.72 moles of iodine to form aluminum iodide. I'm going to start with nothing there. It says how many moles of the excess reactant will remain, and it doesn't tell us which one that is, and how many moles of aluminum iodide will be formed. Okay. So we need to have a 2 to 3 ratio of our reactants if we're going to use all of it. Do we have a 2 to 3 ratio?
No.
What do we have to make this a 2 to 3 ratio?
0.75 iodine.
Yeah, that might be the easiest way to do it is to look at this and say, okay, one part would be 0.25. So I need 0.5 aluminum and 0.75 iodide. Which one do I run out of first? I'm going to run out of the iodide. So this guy right here, this is our limiting reactant. That's the one that's going to control how much we produce. So if that's a limiting reactant, we can identify that now. That's going to be the best one to use to determine how much of the other stuff we use. So we can say, all right, I've got 0.2 moles of iodine, and for every 0.72 moles of iodine, or for every 3 moles of iodine I use, I'm going to use 2 moles of aluminum. So I can figure out how much aluminum gets used. So 2 moles of aluminum for every 3 moles of iodine. Ooh, I2. Handy calculator. My calculator. 0.72 times 2 divided by 3. So I got 0.48 moles of aluminum used. And like we predicted, that's not all of our aluminum. So we're going to use 0.48. We're going to use 0.72. So we're going to have no iodine left. And we're going to have 0.2 moles of aluminum left. How much of this are we going to produce? Do you guys even have to do another problem to solve that? Look, it's got the same coefficient as the aluminum over here. So we can just say that we're going to produce 0.48 moles. So it says how many moles of the excess reactant will remain? 0.02 moles of aluminum. How many moles of aluminum iodide are formed? 0.48.
Wait, how do you use 0.48?
So I know that because those are the coefficients, that if I do the math, it's going to look the same. So if I wanted to do the math, I could go 0.72 moles of iodine, and then using the stoichiometric coefficients for iodine and aluminum iodide, I would say that for every 3 moles of iodine, I'm going to produce 2 moles of aluminum iodide. And it's the same numbers as up here. It's just the units are a little bit different. So it's going to be 0.48. And then moles of aluminum triiodide. Should be I2. I2. All right, what questions do you guys have? Yes, sir.
Can you tell me how you figured out that iodine was the limited reactant?
Yeah, so the way that I was thinking about it is that I knew that I need 2 aluminum for every 3 iodine. But I was comparing that to this 0.5, 0.5 to 0.72. And those aren't the same ratios, right? For it to be the same ratio, this has to be 0.5 to 0.75. And so since this number is smaller than that ratio, then I know that it's going to be less. Sometimes what you'll need to do is take a look at the information that you know and actually solve how much change you're going to get. So sometimes it'll tell you how much you're going to produce. And you need to use the stoichiometric coefficients to figure out what goes in here. Sometimes you have to try both of them. Like there are some problems I can't do in my head, and so I try them both.
And then where did you get the 2 to 3?
It's from the making a balanced equation up here. And so I'm just using the stoichiometric coefficients, just like we did in the last set of problems we did, to be able to figure out what the relationship between those ought to be. Yeah. Yeah. I wouldn't have any left over if this was, instead of 0.5, if it was 0.48. All right, you guys ready to take a stab at these? So what you're going to need to do is take a look at the reaction. The first step, write a balanced equation. Second step, set up a BCA chart because it's going to help you solve problems. You guys have 3 problems to do, right? Number 4, number 5, number 6. And then that's it. That's it.